Hey there, folks, and today we are going to talk about atoms and stuff. There we go. As I was just telling the folks in the room here, this is something that you quite likely had before in life, all right? But the details might be a little fuzzy. We're going to talk about some elements, and we're going to mention protons and neutrons, and that starts to make a handful of you get all twitchy. I promise you, you will not be balancing equations in this class, okay? For those of you at home, I'm giving this lecture in environmental science right now, and whether you're in geology or earth science, we all have slightly different things we do. These guys are going to be talking about elements perhaps a little bit more in depth than we do in my other two classes. You guys, of course, are going to be talking about them in lab, and even here in lecture when we talk about nutrient cycling and so on and so forth, which again we don't really get into in my other two classes. So the last slide kind of summarizes where this applies, and regardless of what class you're in of mine, we touch on a number of these things. But again, across the board, I promise you, you will not be doing any chemistry, math, or anything like that. So don't get all nervous. All right. There is a lot of vocabulary words, though. I won't lie. An atom. Of course, you have a concept of an atom walking in this door. You've probably had a concept of an atom for, many, many years now. But here is an official definition, if you would. And it is the smallest piece or part of an element that still retains the property of that element. Somebody tell us an element or two. Gold. Awesome. What's another one?
Hydrogen.
Hydrogen. Good. Give me one more. Neon. Okay. So the smallest pieces part of neon or gold or hydrogen that still has the properties that you could still recognize if you knew how to recognize it. I'm going to sneeze here, excuse me. The smallest pieces part of that that's still... Thank you. I think I'm done. That still looks like those. It's an atom of it, okay? You go below that, which we're going to do very soon. There's lots of cool stuff to talk about, don't get me wrong, but you'd no longer recognize it as a particle of gold, all right, or anything like that. It loses that definition. So, an atom. All right, now, somebody else, hopefully, get everybody talking today. Somebody else tell me there's three parts to an atom, right? Give me one of them. Three things that make up an atom. A neutron. Good. Now that he's got the ball rolling, fill in the other two. Somebody else.
Proton.
A proton, and what are we missing, guys? An electron. So protons, neutrons, and electrons. Excellent. Now, that isn't one of the test questions, but one of the test, 9 of the test questions are, you need to know three things about each of those. You need to know the charge of a proton, a neutron, and an electron. You need to know where protons, neutrons, and electrons live. And you need to know their mass. All right? We're going to tell you all that, don't worry. But right there, like I said, and then if you already remember this stuff, beautiful. There's 9 points on the next test you know you got already. All right? But more than likely, we get about half of these if we just did a quiz right now. So protons. Who remembers? What's their charge? What are your choices? Your choices are positive, negative, and neutral. What's a proton?
Positive.
P, proton, positive. Good. Okay. How about a neutron?
Negative.
Negative. That's a common answer. Anybody else? Nothing. Neutral. All right. So we got negative or neutral. They both start with N, so maybe that might work. Who wants a tie break for us?
For electron.
Nope, for neutron. We didn't decide on an answer yet.
I think it's hydrogen.
I know. And somebody else thought it was neutral. We need someone to break that tie. Or you guys could just arm wrestle for it. I don't care. All right. Neutron, neutral, NEU, okay? It's got the first couple letters. So let's keep that. And then we're going to tell you where it lives in a minute. There's also a hint in there as well. So neutrons are neutral. It's the electrons that are negative. In fact, the symbol for an electron is an E minus. Okay? All right, so we know our charges. Protons are positive, neutrons are neutral, electrons are negative. Now let's go back to where do they live? Now, earlier when I said there's 3 parts to an atom, that's not exactly a lie, but it's sort of an oversimplification. 2 of these things live in a place called the what? What's in the center of an atom? A nucleus. Awesome. All right. So who lives in the nucleus and who lives outside the nucleus? Anybody, everybody. All right. So protons. Oh, go ahead.
Protons and neutrons.
Live where? Inside or outside?
Inside.
Inside. All right. So protons and neutrons live. They don't live, but you know what I mean. They reside inside of the nucleus. The electrons are swarming around outside like a bunch of mosquitoes. Now, if you've had chemistry, we'll get there in a minute, you learned about those wonderful rings, okay? Turns out they just need that to make the math really easy, or easier, I should say. But nowadays, they kind of look at the electrons as a fuzzy little cloud. As I said, we'll get there at some point. All right, so we got protons, neutrons, and electrons. Protons are positive, neutrons are neutral. Protons and neutrons live in the nucleus. Electrons are negative charge, and they are outside of the nucleus. All that really leaves is the charge. So we'll get to the charge in a minute. So proton, neutron, and electron. We talked about that. All right, here's some official stuff. If you didn't happen to write stuff down, I won't be on here too long because we did say all this. But so a subatomic particle, this is the new part, that contributes mass, 1 AMU. We'll tell you what that is in a minute. It contributes a single positive electrical charge to an atom, and it's located in the nucleus. So positive and nucleus, we knew that already, and now I'm telling you that it contributes 1 AMU. Now, an AMU just stands for atomic mass unit. Don't get all nervous again. It's no different than a gram or a pound. It's just a unit of measure, okay? But it's an AMU. Now, you guys tell me, do you think it's a really big unit? Do you think it's a really small unit? We're dealing with what? Not even atoms here. We're dealing with parts of atoms. So AMUs are really small. You've heard of milligrams, right? This is way smaller than milligrams even. Anywho, a proton weighs, and weigh isn't exactly the right word, is it? Has a mass of 1 AMU. A neutron also has a mass of 1 AMU. As we said, there's no charge connected to a neutron. And it lives in the nucleus as well. Electrons, subatomic particle that contributes a single negative electrical charge to an atom, does not contribute any significant mass, and located on the outside of the nucleus. Now, this is something in my other classes where I've got a lab that talks about matter and mass and some basic vocabulary words that really goes hand in hand with this lecture. Here at Environmental, you guys don't have that lab. So 2 of the things that we review in that class are the definitions of mass and matter, right? And the definition of matter, generally speaking, is anything that has mass and takes up space. You might remember hearing that somewhere along the lines. Okay, matter is anything that has mass and takes up space. And mass, it's kind of circular, but mass is a measure of your matter. All right? So why am I telling you about this? Well, because a lot of times people end up saying that electrons are massless or they don't have any mass. Well, if that were true, for lack of a better word, then we'd be saying that they aren't matter. And they have to be matter, at least as we understand physics. All right? What we can say, however, is that you could have an entire herd of these guys outside of the nucleus, and it wouldn't affect the mass that much one way or another. Okay? Now, it would go crazy with the charge. All those negatives out there, whew, that would really mess things up. So, and that's also what's kind of cool about electrons, all right, is that even though they are practically devoid of mass, they have a huge effect on the charge of the whatever you're happening to make. Now, I mentioned the rings. Okay, I think it's been a long time since I had chemistry, and I wasn't really a fan of it when I did. I really appreciate it now. Don't get me wrong. But anyway, I think it was the Bohr model. Remember that stuff? 1s2, 2s2, 2p6, so on and so forth. And all those rings. And you needed those rings in order to figure out bonding and how stuff, shared and so on and so forth. And it turns out that is like a momentary snapshot of something that happens in a fraction of a second. Because as I said, nowadays, the more they study these things, they've come to realize that electrons really just are these fuzzy, nebulous clouds. All right, and math is hard enough when things are fairly fixed, let alone working with fuzzy clouds. So that's why the reason for that. And at first, I found it really, really frustrating because I struggled with those stupid ring shell things horribly, mainly because I just didn't spend enough time studying chemistry as a student. But and then, to get a little farther and once Wikipedia came around, I started reading all this stuff and everything, and I'm like, wait a minute, so they don't even do that stupid shell thing? And how many, I was really upset. But now I get it, okay? You need it. It's a momentary thing. As I said, it's a snapshot, and without it, we wouldn't be able to understand how these equations go together and all these things that we see in the world. So it was necessary. It was necessary. All right, so that is 9 things about 3 things that you're going to see on the first test. When it comes time, there's going to be a lot of crap that we talk about in between now and then. When it comes time, don't forget to review this slide because you don't want to miss those 9 points. Those are really silly points to miss. All right? Charges for all 3, location for all 3, and mass for all 3. Okay? And plus, that first slide is also a question. There's 10 points right there. Make that a 10 out of 10, you guys. So here's that AMU I was talking about. I am never going to ask you what this number is, but most of you know enough about scientific notation. You see that 10 to the negative 27. Is that a really big number or a really small number?
Really small.
Yeah, really small. And it ought to be, too, right? Because, again, not only are we talking about not just an atom, but we're talking about parts of an atom. So they're not going to weigh a whole heck of a lot.
If it was positive, it would be really big.
Yeah, if it was positive, it would be really big. And this is another thing I go over in my geology, my science classes. I remind you guys, what that negative and the positive, well, there wouldn't be a positive there, but just the lack of a negative means, scientific notation. All right? I was just going to say something. Oh, well, it's gone now. But, so again, don't get freaked out by, AMUs or anything like that. It's just another unit, okay? Feet, miles, grams, ounces, kilometers, they're all units. This is no different. And, again, I'm never going to ask you to regurgitate this number. So. All right, we mentioned the nucleus a couple minutes ago. This is the central portion of the atom. Contains 99% of the mass. Oh, I remember what I was going to ask you. I'll do it in a second here. And again, this is where the protons and neutrons live. Now, a couple times I've slipped up and said, this is how much they weigh. What is the difference between weight and mass? There is a big difference. And it's like the source of all that silliness when you go to those kids' science museums and they say, on Saturn you would weigh I forget if you weigh more or less on Saturn, 5,000 pounds, but on Pluto you'd weigh 3 pounds. And what's happening there? What is weight a function of that mass is?
Gravity.
Yeah. Okay. So weight is gravity's effect on your mass. So yeah, you may lose 30 pounds when you go to the moon or something like that, but unless you lopped off a body part, that you didn't lose any mass. Okay. You just have there's less gravity pulling on your mass, so that little dial on the scale doesn't move as far. All right. So that's the difference between weight and mass. They're not interchangeable. Everyday conversation, sure, you could probably do it. But in a science class like this, it's worth taking a moment to point it out. So mass is a sum of your matter. It is supposed to be aside from gravity. Mass is a sum of your matter. Yeah, just make sure I didn't say weight there. Okay, I've used this word a handful of times. Again, I don't know if I told you guys or not. I know I told a couple of my classes. I went through a good day and a half one year talking about, a lecture and a half one year, talking about cosmology, how the universe comes together. And I had used a word, probably a dozen times, and the word was galaxy, okay? And I just assume that you guys know what galaxy means and so on and so forth. And that's an example of a galaxy, exactly. And finally, at the end of the second day of me talking about all this stuff, a student raised their hand and said, I just want to be sure, what is a galaxy? I'm like, oh my God. And I felt horrible, Not everybody walks in, and I'm sure I said this to you guys on day one. Not everybody walks in with the same vocabulary. So, just for the halibut here, let's subatomic, all right? It means smaller than an atom, below the level of an atom, and that's what sub means, okay? You've heard that prefix before, subpar. Submarine is something that goes below the water, okay? Substandard, and so on and so forth. So, subatomic just means below the level of an atom. You could spell it a couple different ways. And like I said, just wanted to point that out. Mainly because we're about to go sub-sub. So, elementary particles. I say this sort of joke every semester, and nobody really laughs, but I don't know why we call them elementary particles instead of elementary particles. You guys don't go to elementary school, but
pronunciation.
It is. It's just a different pronunciation, and I don't know why, but we say elementary. Okay. So elementary particles are subatomic particles. A definition, I guess, would be the best bet would be the second bullet here. It's a particle not known to have substructure. There's that word again. They are the basic building blocks of the universe. So, elementary particles come two kinds. We've got quarks and we've got leptons. Not going to worry about leptons too much. I will refer to one kind of lepton. What did I tell you a few minutes ago that E- was? It stands for something. I just heard it. Electrons, yeah. So electrons are a type of lepton, okay? And then we got to figure out what quarks are here. So what's going on is a ways back, like the 60s. At first we thought an atom was as small as you could get. Then they realized that atoms have pieces, parts. And we got your protons, your neutrons, electrons. Then, a handful of decades later, they realized that, there's stuff smaller than protons and neutrons. And they were these elementary particles there, and specifically right now, quarks. Okay? So quarks are the pieces parts that make protons and neutrons. And at the moment, remember our conversation the other day about the nature of science? At the moment, we don't know of a smaller substructure. God willing, I'm still teaching in 20 years. Maybe I'll be talking about the pieces parts that make up quarks. You never know. You've heard of particle accelerators, right? Those are basically racetracks for physics geeks. And they're zooming protons and whatnot around in really, really fast circles and hoping for a car crash. And in those car crashes, they're going to break into their pieces parts. And the idea, they just built a new one, it's been 10 years now probably, in Switzerland, even bigger than, we've had one under Chicago for years.
Oh yeah, the one in Switzerland. You told us that one too.
Yeah. So the one there, it's CERN, all right, and it's a Large Hadron Collider. See that word hadron there. They're constantly doing this, and that's why I feel if it's going to happen, it's going to happen. We'll find something that makes up quarks at some point. But for now, this is what we got. Don't worry about the word hadron. All right, you got enough vocabulary floating around. I do want you to remember what a quark is, though. All right, a quark is one type of elementary particle, and a quark is what we make protons and neutrons out of. So, there was another word at the bottom of the first slide, and that was that lepton word. And remember, I said we're not going to worry about that too much, except you know that they're a type of, that electrons are that. So electrons just are. In the beginning, there were electrons and there were quarks at this point, as far as we know. Also, something you may have heard that word, neutrinos. All right. Not that I'm aware of. It is possible, but so neutrinos are also a type of lepton, but again, they don't concern us right now. Just since I bothered to make the slides, I figured I'd give you, the real words and all that stuff. So you want to know that, remember this is all a sub-conversation, there's that sub again, of the atom thing. So we had protons, neutrons, and electrons. Atoms are made up of elementary particles. Electrons are already elementary. Protons and neutrons are made up of quarks. Gabish, you good?
Yes.
All right. What were you guys doing in 2011? How old were you?
I was 7.
7. All right. So you weren't paying much attention to things, maybe.
Of
At
course,
least about this. So I was teaching well before 2011. I was teaching in the mid to late 90s.
It can also be called
So-
2011.
So, yeah, yes it could. So back then, I used to say, it hasn't even been 100 years that we've known about atoms. Well, I think it was Plato that put forward the idea of atoms. We've known about atoms for a while,
The Greek
but
philosopher.
yes, it was him or Socrates. I'm not sure. I think it was Plato. Anywho, so what Ernst Rutherford did about 100 years ago, now 110 years ago, was that he gave us this idea, this concept of an atom that we know and love. Okay, the nucleus, the protons and neutrons in the nucleus, the electrons outside of it.
113.
Sorry?
113 to be exact.
Thank you. We've got him to thank for that. All right. That there, and we all recognize that. That's sort of your stereotypical 1950s and 60s atomic symbol sort of looking thing. All right. And oh boy, they were just the population was amazed. That and space flight, right? They were just the two biggest things going on.
Wait, what's space flight? Space flight. What's space flight?
Flight, space, going into space.
Oh, the space race?
Yeah.
Some beauty.
So, atomic structure. All right, about 100 years old. And if you didn't get what we meant earlier about protons and neutrons being in the nucleus and the electrons zooming around it, there's a great visual. Thank you, Ernst Rutherford. Okay, another vocabulary word for you. We already talked about elements. We told you on the very first slide that an atom was the smallest part of an element that retained the properties of that element. Well, again, that's taken for granted that you know what an element is. So let's tell you right here that an element is a substance that cannot be broken down into other substances by ordinary chemical methods.
What about the periodic table of elements?
So we're going to, you guys already gave me a handful of elements earlier. I think we had gold, we had hydrogen, and we had the one of the gases there, the noble gases, neon maybe. All right, there's about 100 and some more. All right, again, you've known about those. You might even know some of them, they have an atomic number. You might even know that about them. We're going to show you a table here. He mentioned the periodic table. Well, there it is. All right. So what we've got here, and you look at this, and a lot of people who don't know too much about it, and why would you? You got to wonder. Okay, it's not alphabetical. Maybe it's the order that they're discovered. Maybe we don't know. Who does know? How is this arranged? What's the sense here? Yeah. It is sort of by mass. Very close. What's another number that's on here, though? That's related to the mass, but...
The atomic number?
Yeah. All right. The one at the top, which is really small, and you guys can't barely see it. I apologize. But, so, in a nice, simple, basic periodic table, which is what I always try to show you guys, there's really only like 3 things, 4 if you count the name. All right, you've got the symbol for the element. Then there's a number at the top and the number at the bottom. The number at the bottom that he mentioned a moment ago is the atomic mass, and we're going to talk about that really soon. The number at the top is what I want to talk about right now, is because for the most part, all right, these are arranged in numerical order. Hydrogen 1, helium 2, lithium 3, beryllium 4, boron 5, carbon 6, nitrogen 7, oxygen 8, iron 9, so on and so forth. That's their atomic number. And you're going to see a slide about this in a moment or two, so you don't scribble it down now, you get it then. All right? That is the number of protons. So that's how this is arranged. They're simply adding one more proton to each of these, and we're making a new element. Now, as some of you may already know, and some of you will learn soon, when you add a proton, 9 times out of 10, you're also adding a neutron. And that's where the atomic mass comes in. The mass is the sum of the protons and neutrons. They're the only 2 things that have measurable mass. And because we tend to add these things evenly, again, 9 times out of 10, not always, but the most of the time, your mass is going to be twice your number. So we would expect carbon, who's 6, to have a mass of 12. Nitrogen, whose atomic number is 7, to have a mass of 14, and so on and so forth. All right? Now, what the different colors are for, why they pulled those 2 strips out at the bottom, go ask a chemistry teacher. Doesn't concern us, okay? But there is reason for all this organization. It does get deeper than just adding protons, but that's all we need to worry about. All right? So that's what's going on here. And again, you've seen the periodic table. Don't worry, you don't have to memorize it. Not in any of the classes I teach at any rate. But you do kind of, it's good to be familiar with it. It's good to be familiar with it. We use it for minerals and rocks. We use it for looking at the atmosphere. And again, you guys use it in here in environmental science. We're going to use it for atmosphere. We're going to use it for nutrient cycles and stuff like that. Okay, you're going to see some of these elemental names. So, and also with air quality, water quality, pollutions, right? Some of these nasty chemicals are made up of huge strings of these symbols. Another vocabulary word, compound. So a compound is a substance formed by the chemical combination of 2 or more elements. Somebody tell us a compound. Give us one. You probably have one sitting in front of you right now. We've definitely got that coming out of our mouths. Carbon dioxide is a compound. Give me another compound. Well, water is one that usually comes to mind really easily. And another one that most people know is salt. All right? But CO2, I haven't heard that one in a while. Definitely a good one. So what's cool about a compound, all right, is that when you add carbon and 2 oxygens together, or 2 hydrogens and an oxygen, that it makes something new, it makes something special, it makes something different. It gets new properties, and that's, I don't have a better word for it other than magic. That's the magic of a compound. So what we have here on the right, again, is usually one of the first ones that people mention is salt. All right, what are the two ingredients in salt? Somebody remind us. What's the formula for salt? Nobody, really? All right. Well, salt is composed of two things, sodium and chlorine. You may remember NaCl, right? Na is sodium, Cl is chlorine. We call it sodium chloride, but the element is chlorine. So here's the neat magic. That's sodium in the upper left-hand corner there. It's a solid, semi-metallic-y looking thing, but here's the weird part. It's incredibly flammable, nasty stuff, sodium is. Down below it, we've got this. You maybe can't tell if it's a liquid or what it is. That is a bottle of greenish yellow gas. That is chlorine. All right. Not nice at all. So you mix this flammable, semi-metallic gray solid and this yellow gas together, and it makes French fries taste good. Wow, mind blown, right? All right, that's the magic of compounds. How does it happen? Again, go ask your chemistry teacher. But it gets new properties. It acquires new properties. Water's another one. Water is amazing when you really stop and think about it. All right, first of all, it's like the only substance that exists in all three phases naturally at the surface of the earth, natural conditions. All right. But hydrogen, what is hydrogen? Hydrogen is a gas. Oxygen is a gas. So you take two gases, you mix them together, you get another gas. Okay, that's not too surprising. But a gas that could also be a liquid and a gas that could also be a solid, all without doing anything really strange to it other than changing the temperature. So that's pretty crazy too. We take it for granted. You've been surrounded by it for 20 some years. But it is amazing as far as that goes. So that's what's cool about compounds. All right. We started this whole presentation half hour ago-ish by talking about an atom. And we told you that the atom was the smallest species part of something that you can have and still recognize it as that something. Well, now that we've introduced the term compound to you, atom doesn't really work anymore. All right? We need to use the word molecule. So that's really the new vocabulary word here. The thing is it's essentially the same definition, and I wrote it that way on purpose. The only thing we're swapping out is instead of an element, it's of a compound. So a molecule is the smallest pieces part of a compound that retains the properties of that compound. Like I said, exactly the same. And you think about it, you hopefully wouldn't say an atom of water, an atom of salt. This doesn't even sound right? But molecule, a water molecule, a molecule of salt. So it's almost a pluralization rule. So if you have one ingredient, you use the word atom. If you have two or more, we use the word molecule. Okay? Okay. Lively bunch today. All right, so we're back to the periodic table here for a couple minutes. And I've got a little excerpt of the periodic table over there on the side. And we even mentioned this number already, the atomic number. And we said that the atomic number is usually at the top, and it's usually in the center. For whatever reason, the one that I picked, the atomic number is slightly off to the side. But, well, it's slightly off. It's in the corner. But we told you that this is the number of protons in any given element, okay? As you see on here, silicon has 14, phosphorus has 15, sulfur has 16, chlorine has 17, so on and so forth. And you really can, at this level at any rate, still keep thinking about that whole Lego sort of effect. You're building one by one onto each other.
Same concept.
And the important thing we want to add here is that this is what defines the element. All right? if you took a proton, if there was a way to do this, if you took a proton out of nitrogen, it wouldn't be nitrogen minus a proton. It would literally be carbon. All right? The atomic number defines that element. The number of protons defines that element. Now, this segues into our conversation about atomic mass. All right, I told you that for the majority of the time, the atomic mass is going to be twice your atomic number. And if these numbers were big enough, you could actually see it. You'd look, and sure enough, carbon at 6, its mass is 12. There's always going to be a decimal point. Don't worry about that. Nitrogen is 7, so its mass is 14. Oxygen comes in at 8, so you're looking at 16. And that's a good general rule, as I said. You like to match up the protons and neutrons. It just keeps the element happy. All right? However, it doesn't take long for you to stare at the periodic table and come across something where the atomic mass is not twice the atomic number. As it so happens, I've got one on here. The bottom right-hand corner there, krypton. All right, it has a atomic number of 36. So we would expect its mass to be what? Somebody help us out there. 36 and 36 is awesome. 72. Yeah. All right. So sure enough, I can't see that far either. Krypton is 83. 83, not 72. What did we add to make it way more? Is it protons? Is it neutrons? Is it electrons? What did we add? Protons or neutrons? It's got to be one of them. It's got to be one. Why can't it be protons? What would happen to this krypton if we added a proton to it? Into whatever's next, right? Remember, if we mess with the number of protons, we mess with the element. It's no longer that element. So the only thing we can add are neutrons. Okay? So when something is heavy like this, as we could call it, it's because of extra neutrons. Now, they have a vocabulary word for that. Well, actually, we got a slide here first. So atomic mass, if you didn't get it down, we've talked about it 3 times already. The sum of the protons and neutrons, and typically twice the atomic number. We just said that. So when that's not the case, the word they have for that is an isotope. Another word you've heard. Okay. They give us the example here of carbon-12, carbon-13, and carbon-14. And what they're doing is adding a neutron each time in order to increase that mass. Now, as we said, the majority of the elements that show up on the periodic table, they do follow this rule we've been talking about. But that kind of is misleading because there are a lot of isotopes out there. All right. What they tend to do, at least what I'm told, is that they put the most stable versions in the periodic table. Stable version of the element, which oftentimes isn't an isotope. Sometimes, okay, but oftentimes it's not the isotope. So, at any rate, you will see a few here and there. If carbon-12 or carbon-14 sounds familiar to you, you probably spent some time watching Discovery Channel or Nature or one of those TV shows. Anytime they're talking about some recent stuff that they're trying to date, mummies or a mastodon they pulled out of ice, they're using carbon dating, okay? And that's where this comes in. Again, in my geology class, not so much in earth science, and not so much in environmental, we do talk about geologic time. We try to get across, no matter what class we're in, that the Earth has been here a very, very long time, and these processes are huge.
Earth has been longer than we have.
What's that?
Earth has been here longer than we have.
Yes, it definitely has been here longer than we have. We don't talk too much more about isotopes in here, but you might see, one here or there. So isotope.
And art will continue to exist without it.
Yes, hopefully.
Uh,
So why did we spend time to do this? All right. As I said, it varies with the class that I'm teaching, but some of this touches on all of these. All right. Atmospheric studies. The atmosphere is made out of elements, is made out of compounds. All right. When we want to talk about in this class, talk about pollutants, be it in the atmosphere or in the water, we're talking about these elements. Environmental concerns, mentioned that. In both classes, we're living on the earth, we're talking about the earth. These are all earth science classes. Okay? Minerals are made of elements. Rocks are made of minerals, and guess what? The earth is made up of rocks and minerals. And again, surrounded by this atmosphere. So everything we do, talk, see, look at, scratch, sniff, whatever,
Ocean.
everything is composed of this stuff. So I did take some time to back up and make sure you guys, kind of remember this stuff before we move on and just start throwing out stuff that I assume you knew or heard before or something like that. So that's why we did that, and that's why we took some time. Now, one thing I am going to ask of you guys, I always tell you I don't have homework in here, and generally speaking, I don't. When I present these lectures to the folks online, I oftentimes have a handful of YouTube videos that go along with it to sort of expand on the content that we've talked about in here. I don't have those offhand right now. For me to find them, it'd sit here 5-10 minutes, me digging through this, that, or the other thing, trying to find them. I'm going to post them on our site, okay? And you folks at home, you'll have these somewhere as well. Please take 10-15 minutes and watch them, all right, before we meet again. And again, it just takes the content a little further, some application level stuff. And I think this is the one, there's even just a super short writing assignment that goes along with one of these. So it's about, it actually goes back to the nature of science conversation we had the other day. And it talks about some early scientific thinkers. So please keep an eye out for those. I will post an announcement to let you guys know that they're there. So, and where to find them. All right, so I'm going to wrap up this recording here, and we will move on.